Hi! In episode 12 of Crash Course Physics, it was all about torque. And there's actually a related notion that got mentioned at the end of the episode, but is maybe a bit more central than torque, more fundamental. That's angular momentum. So let's make it a little bit bigger. And let's start with angular momentum. Angular momentum is the one quantity that describes circular motion just as momentum describes linear motion. It is a conserved quantity, and we've seen something very similar, something very close to a proof in an earlier episode on uniform circular motion. Geometrically, angular momentum can be thought of as the area spanned by the position and momentum vector. And since this is a parallelogram, and we think of the area as base times height, we can actually think of it as the product of the distance from the origin times the perpendicular component of the momentum. If you've studied mechanics maybe a little bit further, you might recognize that this is actually the vector product or cross product between position vector and momentum, and that the angular momentum is a vector quantity. If we really think of three-dimensional motion, not just in a single plane, but in all kinds of axes, then the angular momentum actually describes the rotation around all three coordinate axes. If we just look at uniform circular motion, the momentum is always perpendicular to the position vector. So L is just the product of P times R. But momentum, we've learned, is the product of mass times velocity. And velocity, we have learned, in uniform circular motion is just angular velocity omega times r. So the angular momentum is m times omega times r squared. And what we do conceptually is to unify mass times the square of the radius into a single quantity called the moment of inertia. So now this relationship L equals I times omega is analogous to the relationship of momentum equaling mass times velocity. If we have not just a single mass point, but a more distributed mass spinning around a single point or an axis, we actually sum up all the moments of inertia of any single point in this distributed mass. So it will be an integral over the whole space of the square of the radius times the mass density rho at a single point. Now the notation that they used in the episode was actually integral of r squared dm. This is because this product of mass density times a tiny little piece of volume can be thought of as a unit piece of mass. Density times volume equals mass. In the case of accelerated circular motion, so the radius stays the same, but the mass point starts getting accelerated. Now this vector here represents the force that is applied always tangentially to the position vector. Then the change in angular momentum is radius times the change in momentum. We know that the change in momentum is F times delta t. So the change in angular momentum is driven by the rate of change R times F, which we now call torque. So torque is the rate of change of angular momentum, just like force is the rate of change of linear momentum. Now for torque, we can also find a more useful relationship, remembering that force is m times acceleration, and acceleration for circular motion is angular acceleration alpha times the radius. We get this relationship and recognize again the moment of inertia. So now we have the relationship torque is I times alpha, which is the rotational analog of force being mass times acceleration. And in the previous slide we had the relationship angular momentum equals moment of inertia times angular velocity, which is the analog of p equals m times v. Finally, now let's look at this little thought experiment of three objects sliding and rolling down an inclined plane. We can analyze this situation with the rotational kinetic energy. This is the formula, and it is completely analogous to translational kinetic energy. So it's not very hard to prove this relationship. And see that part of the potential energy gets converted to rotational kinetic energy instead of translational kinetic energy. So the contribution, the energy at our disposal for moving the whole object downwards is smaller. So it takes more time to go down. But there's also a more qualitative explanation of why the ball and the ring take more time to slide down the inclined plane. It is because there are always parts of these objects that get accelerated back up. So they take overall more time to go down the end of the plane. In the case of the sphere, it is proportionally only a part of the sphere that gets accelerated up. So for example, the center of the sphere is just sliding down. In the case of the ring, just about half of the ring is moving upwards at any given point. So it is the one object that takes most of the time to reach the end of the inclined plane. So that was it for this episode. Don't forget to subscribe, follow me on Twitter. See you next time.